Hello and welcome back. We'll finish up section 9.1 in this video. Let's look at another example where we're comparing proportions using two samples. So in a medical study, we had 11,037 people were given aspirin, and 11,034 people were given placebos. And then during the study, they found that 139 people had heart attacks amongst those who were given aspirin, and 239 people had heart attacks amongst those taking placebos. So the question here would be, we want to test the claim that those people that took aspirin had a reduced risk of heart attack than those who were taking the placebos. And because this is a medical study, we have a pretty small significance level, 0.01. So we want our results to be confident that we're not making a mistake in our results. So we want to test the claim that aspirin reduces the risk of heart attacks. So this is our claim. Aspirin reduces the risk of heart attacks. And symbolically, if we call P1 the probability of having a heart attack while taking aspirin, and P2 the probability of having a heart attack when taking a placebo or not taking aspirin, we would want to say that the probability that probability that we have a heart attack when taking aspirin is smaller than the probability of having a heart attack when we're taking the placebo. So P1 is taking aspirin, P2 is while not taking aspirin. The null and alternative hypotheses. So again, the null hypothesis is going to be that P1 is equal to P2, null hypothesis being when those are equal. And the alternative hypothesis, we will use this when P1 is less than P2. So our significance level was 0.01, and now we need to find our test statistic. And again, this is a pretty complicated formula, so we're just going to use StatCrunch. So when we come to statistics, we can look at proportion stats because we're comparing proportions. We have two samples, and we don't have the individual data values for every person, whether or not they had a heart attack. We only have summaries. So we saw that there was 139 individuals that had heart attacks while taking aspirin, but there were 11,037 people who were taking aspirin, as opposed to the 239 people that had heart attacks while taking placebo, and among the 11,034 people who were taking the placebo. Our hypothesis test, our null hypothesis, was when P1 is equal to P2. But if P1 and P2 are equal, that means that their difference is 0. This is just the way that they write it here. And our alternative hypothesis would be that P1 is less than P2. So when we look at these values, if I come back, I can rewrite my alternative hypothesis here, the following. If I just subtract if I subtract P2 from both sides, we have P1 minus P2 should be less than 0. So again, I've just subtracted P2 from both sides, and I got this. And this should be what the alternative hypothesis is, that P1 minus P2 should be less than 0. If P1 is smaller than P2, when we take the difference, we should get a negative number. And again, I will plot the p-values just as an option so that we can see the big picture. So if we compute this, we have everything that we need. Our test statistic is our z-score right here. So that's going to be negative 5.19, which we can write here. negative 5.19, and the p-value is so small it's less than 0.0001. So they didn't compute the actual value there, but the p-value itself is going to be less than 0.0001. But if we compare this to the significance level, the p-value is certainly much less than the significance level. So we reject the null hypothesis, which was h0. So if we reject h0, that means that our null hypothesis, or sorry, our alternative hypothesis is true. So we can conclude that P1 is in fact less than P2. So our conclusion, there is sufficient evidence to support the claim that aspirin reduces the risk of heart attack. Now, we've already seen that, okay, so this is quite nice, and we're using p-values, which we'd used before, but we can also use confidence intervals to do the same thing. So with confidence intervals, again, there is a formula for all of this, but I'm simply going to use StatCrunch. So if we come back to StatCrunch and we open up stat, we can come down to proportion statistics. Everything is exactly the same. We have two samples, and we have a summary of the data. There were 139 heart attacks amongst the 11,037 people taking aspirin, and there were 239 heart attacks amongst the 11,034 people taking placebo. We don't want to perform a hypothesis test, we want to perform a confidence interval. And the confidence level, so if we come back here, the significance level was alpha, which is 0.01. So the confidence is going to be 1 minus alpha, which is going to be 0.99, as in we want to be 99% confident about our answer. So our confidence interval is going to be 0.99, and let's plot the confidence interval itself. So we will compute, and again, all of our data is right here. And then we see that we have our lower limit and our upper limit is right here. So the difference in proportions, P1 minus P2, we are confident is somewhere between these two numbers. So that's negative 0.13, let's round to 6. So negative 0.0136. So P1 minus P2 is somewhere in between this number and negative 0.0046. So what is the conclusion that we can draw here? Well, 0 is not in this interval. So 0 is not in the interval. So what does this mean? This means that P1 minus P2, we are confident, is not 0. So we are confident that P1 and P2 are not the same number. So we get to reject the null hypothesis that P1 is equal to P2. Furthermore, we can say the following. P1 minus P2 is negative, which should indicate that P2 is the bigger number. We take a number and we subtract something that's bigger from it, we'll get a negative number. So our conclusion is that there is sufficient evidence to support the claim, and you'll notice this is, you should be getting deja vu, there is sufficient evidence to support the claim that aspirin reduces the risk of heart attack. Okay, so we achieve the same conclusion using confidence intervals or using p-values. And again, everything is just within StatCrunch. So if we click over, we can see the confidence intervals sort of drawn out. So if here is 0.008, 0.006, so 0 will be off to the right and is not contained in the confidence interval. So we do not expect P1 and P2 to be the same number. We'll finish up this section just by mentioning sample sizes very briefly. So this formula here for a sample size that gives the required size of error at the correct confidence level, this can be deduced by going back and looking at the formula for the error, but here we've just solved that for n. So if we want an error that's as small as e, so we want this big of an error in our confidence interval, and the confidence is 1 minus alpha, we need a sample that is as big as this. So we take the critical z value, square it, divided by 2 times the error squared. So let's just apply this to an example. So let's say that we want to compare the proportion of men and women who use smartphones. So again, we're comparing proportions, and we want a 95% confidence interval, and then the error should be 0.03. So with our formula, n is equal to this critical value squared divided by 2 times e squared. When we look at this critical value, we are, let me draw this on the next line. So with a 95% confidence interval, what we're saying is that we want 95% of the values to be in there. So what we need is the critical value, which should correspond to right here. So for instance, if we go to StatCrunch, open up our normal calculator, normal distribution calculator, we want the area to the right, and we want that area to be half of 0.05, so 0.025. And we see that we get 1.96. So this is going to be 1.996. So our formula is simply going to be 1.96 squared divided by 2 times e, which is 0.03 squared. And if we do this, we get 2,134.2, but we can't have 0.2 of a person. So in order to make sure that we have as big a sample as we need, we want to round up. So 2.35. Even though this would normally round to 34, we want to round up to 35 to make sure that we capture exactly what we need. We need 0.2 of a person, so we'll just use a whole person instead. And that's all there really is for computing the size of a sample. The other thing to keep in mind is that we'll need a sample of men and a sample of women. This n refers to both samples, so we would need 2,135 men, and we'd need 2,135 women. This doesn't differentiate between the different samples, but it does tell us what we need for both samples.